Hello and welcome to Stochastic Ways. Today we will be talking about two exact line search methods, bisection and golden section. Both these methods to work, the function have to be unimodal inside a given interval. Now the question is, what does unimodal mean? It's very important. Let's take the example x squared and check whether it's unimodal on the interval -1, 1. We know that the minimum of this function occurs at the point x equals 0, and for the function to be unimodal, it must decrease until it reaches the minimum, and then start increasing. Now from -1 to 0, it's decreasing, meaning the derivative is negative, and strictly increasing from 0 to 1, meaning that the derivative is positive. Therefore, we can say x squared is unimodal on the interval -1, 1. And in simpler terms, unimodal means that there is a unique minimum inside the interval. Now let's do a simple example of bisection. For this algorithm to work, we need to specify three things: the interval we are working on, how far we move to the left and the right, and the precision we want. And the rest is a piece of cake. We start by calculating the midpoint on the interval. From this point, we take a step to the left and step to the right, each with a length of epsilon. This gives us two new points called lambda and rho. Next, we compare the two values. The idea is simple. We discard the side of the interval where the function is larger because the minimum is more likely to be on the other side. So we update the bound of the interval by moving the edge corresponding to that large value inward, effectively shrinking the interval and getting closer to the minimum. We keep repeating this iteration until we reach desired precision. Let's now look at the golden section method as an example. It's basically the same as the previous method, but it's a bit more efficient. The golden section takes different inputs. We present a new constant called golden ratio. We won't be working with this value, but with the derived version of it, which is the golden ratio -1, and we will call it R. And the new value is basically the epsilon of bisection. It's basically the step. Same as bisection, we precise the interval where the function is unimodal and the precision we want to achieve. The algorithm is pretty simple. The idea is pretty simple. Starting from point A, we take two different steps, each placed proportional to the length of the interval, one at approximately 38%, and we call it lambda, and the other at 61%, and we call it mi. We compare the results and remove the side where the function is larger, just like in bisection. In the next step, the golden section shines with a simple approach that saves a lot of work by reusing the function values from the previous step. We just swap the roles of lambda and mi and keep repeating this iteration until we reach the desired precision, meaning we get close to the minimum.